Okay, so today we're going to learn how to do two-step mole problems. You just learned how to do one-step mole problems. Now, the key going forward is going to be how do you tell the difference between a one-step mole problem and a two-step mole problem. And one of the things you should have recognized is when you were doing one-step mole problems, every single problem had the word moles in it, whether you're converting from grams to moles or moles to grams, or whether you're going particles to moles or vice versa, you always saw the word moles. So if I see a problem like this, how many molecules of iron 3 carbonate are there in 19,000 grams? You can clearly see that we're listed the units of molecules and listing the units of grams. Nowhere in the problem do we see the units of moles. That's okay. What we're going to do, and what's a really smart strategy often to take, is let's take this new type of problem and make it look like something we know how to do. So let's pretend that we don't care about molecules. If you're given grams, you know how to convert grams to moles. You know to use the formula mass for that. And so that's our first step that we're going to do when we get to this mathematically. Now, before we do that, to find the formula mass, we have to know the formula. So the formula for iron 3 carbonate is iron 3 is a 3 plus charge, carbonate is a 2 minus. So the formula for iron 3 carbonate, Fe2CO3, 3. You should be pretty well versed at writing formulas at this point. So now that we've got this formula, we can start setting up our work. We'll set up the work of 19,000 grams. And then remember, put the formula after this. This is really going to serve you well when you get to a future unit called stoichiometry, where that last name or the formula written down is so helpful. So we've got 19,000 grams of iron 3 carbonate. Now remember, we want to get to molecules eventually. Let's not worry about that. Let's just convert to grams to something we know how to do. We know how to convert grams to moles. And as we just said before, we're going to use the formula mass. So we're going to put moles in the numerator and grams in the denominator. We do that so the grams can cancel. And notice we've just converted to moles. Even though we haven't done the math yet, that's fine. To get this number, you know to find the formula mass. So we'll set up our work for the formula mass. The three different elements in iron 3 carbonate are iron, carbon, and oxygen. Iron has a mass of 56. There's 2 of them in the molecule. And then carbon has a mass of 12. There's 3 of those in the formula here. And then oxygen, you probably know already, is a mass of 16. And there are 9 of those in the formula. So when we add those up, we get 292. Now, remember, since we're doing unit analysis, we need to put units here. The worst thing you can put here is grams, because this is not a mass. It's the mass of the formula. The formula is written for that many grams per 1 mole. So write those units down here. So you notice the 1 goes with the mole, and then we have 292 grams. Now, in a one-step mole problem, we would calculate and be done. But in a two-step mole problem here, we haven't gotten to the units we want. We have gotten just to the units of moles. So instead of stopping and calculating and writing down a bunch of calculator stuff, which is just time-consuming, we keep going. We now know moles, and you've had practice of converting moles to molecules. So you know to convert from moles to molecules, you need to use Avogadro's number. So moles of iron 3 carbonate needs to go in the denominator, because that's the unit we're in right here, and we just need to use that moles in the denominator to cancel. And we want molecules, I'll use MLC for molecules, of iron 3 carbonate in the numerator. Now remember, the 1 will go with the mole, and there are 6.02 times 10 to the 23rd molecules of iron 3 carbonate in 1 mole. Now we'll cancel out the moles, and we'll see that the only unit that we haven't canceled is molecules. And this is why it's called a two-step problem. We use one of the steps as the formula mass and the other one of the steps as Avogadro's number. In a two-step problem, you're going to be using both of these conversion factors that you've seen until you learn more chemistry and other ways to convert to and from the mole, but still you'll always use two conversion factors. Now the math is just slightly more difficult, and here's how I recommend you do that. I recommend you take anything in the numerator and you multiply those numbers first. So 19,000, clearly you won't do times 1 on the calculator, but if it was a number other than 1 later on, then you would just multiply by that. And then times 6.02 times 10 to the 23rd. Remember that when you're typing this in the calculator, that you want to use that EE key. So if you're typing the calculator, you'll do 19 times, not the 1, 6.02 EE 23. And I don't like to hit enter here because if I make a mistake, it's harder to fix. So I'll just now divide by anything in the denominator. So I'll divide by 292. And if there was something more other than a 1 here, I would divide by that number. If it was a 3, I'd divide by 3. This way I can do it all in one line on my calculator. I don't have to worry about parentheses. And it's easy to fix if I make any mistakes. So when you type this in, you should get about 3.917 times 10 to the 25th molecules of iron 3 carbonate. But you know you're not done here with the calculation because we have to watch significant figures. Remember, formula mass and Avogadro's number, they don't count as measured values for us, so they don't count for sig figs. Only this 19,000 grams, which is right around 40 pounds or so it's quite a bit, has 2 sig figs. These zeros are not significant because they're not underlined and there's no decimal after them. So we only need 2 sig figs. So the 3 is the first sig fig, the 9 is the second one. So it will round to just 3.9 times 10 to the 25th molecules of iron 3 carbonate. So the key here again is recognizing that there's no moles in the problem, and so since there is no moles in the problem, we're going to put it there. We're going to get to the mole, and then we're going to convert out of the mole. That's your whole process for a two-step problem. Get to something you're comfortable with, the mole, then get out of that unit by using the other conversion factor. So let's try another problem here. So last time we were given mass and asked molecules. For this problem, we are asked about mass and we're given molecules. So we can see right off the bat it's not a one-step because we don't see the word moles in there at all. So we're going to do 2 one-step problems back to back. Now, of course, we need to write the formula for magnesium hydroxide. Magnesium is a 2+ because it's an alkaline earth metal, and hydroxide, you can look up, is a 1-. So to equal out those charges, we've got 1 magnesium and we have 2 hydroxides. But be careful if you write the formula like that. That says just 2 hydrogens. You need those parentheses. That's a very common mistake. So let's go ahead and process this problem. We're going to start with what we're given. 7.560 times 10 to the 19th molecules of magnesium hydroxide. Now, we want to get that to mass eventually, but we don't have a direct conversion between molecules and mass. So we're going to do what we know how to do from before. We're going to convert molecules to moles. We're going to do a one-step problem. We won't finish it there, but let's do one step because we know how to do that. So the 1 goes with the mole, and you know there's Avogadro's number of molecules in 1 mole. So cross out your units as you go, cancel those out, and you'll see the units that are remaining. That's really helpful to keep track of where you are in these more challenging problems. Now you're in moles. We want to get to mass. So you just have to ask yourself, how do I get from moles to mass? The only other way that you know how to convert out of moles right now is formula mass. So we're going to find the formula mass for magnesium hydroxide. So rounding magnesium's mass to the nearest whole or half, it rounds to 24.5. There's only one magnesium in the formula. There's oxygen, which we know is 16. And because we remembered those parentheses in the formula, we're going to now remember that there's 2 oxygen atoms in this compound. And then we have hydrogen, which has a mass of 1, of course. There's 2 of those for a mass of 2. Now, the formula mass here is 58.5 grams per 1 mole. Remember again, put the grams per mole. Okay, so we're going to use the formula acid. We'll set that up using unit analysis. You can see that we've got moles in the numerator, so now we need moles in the denominator. And remembering that formula is going to be really, really, really important as you're going forward. It's not critical to do mole problems correctly all the time, but when we use these mole problems for more realistic type chemistry, something called stoichiometry, you are going to want those formulas on here. And then we put the mass in the numerator, 58.5 grams for every 1 mole. And if I do this right, we've got moles in the numerator, canceling with moles in the denominator. The only unit we have left is grams, so now we know we're in mass and we can just calculate. So when you type this in the calculator, again, multiply the numbers in the numerator together and then divide by the numbers in the denominator. Now be careful when you have Avogadro's number in the denominator. You have to use that scientific notation. So many times people try to resist using scientific notation, and then they're getting these crazy answers that don't make sense because they're not trying to learn the new method of using the calculator. So when you type this in, we're going to get a small number because times 10 to the 19th is very small compared to 1 mole. So before I write down some of the calculator junk, I'm going to plan ahead. Looking at my start, I see I have 4 sig figs. Remember, this 0 is significant because it's after a decimal point to the far right. So I'm going to write down at least 4 sig figs. I like to write down a couple extra. Those zeros are not significant because they're to the left of your first non-zero digit. So I know I need at least 4 sig figs. I like to write down 2 extra all the time just because if I do something with this number, it's going to eliminate extra rounding error from using a rounded number. So my first sig fig is the 7, the second's the 3, third is the 4th, so the 6 is the 4th sig fig. So we're going to have 0.00, remember those are not significant, 734. Now the digit past the 6 rounds it up to a 7 grams of magnesium hydroxide. So that is the mass of magnesium hydroxide that would be in this many molecules of that compound. So these are the 2 basic types of 2-step mole problems that you'll see. So just to summarize, you have to make sure that you are looking to see is moles in the problem or not. If moles is one of the units, a 1-step problem. If moles is not, it's most likely a 2-step problem, and then you need to use both conversion factors that you know up to this point, Avogadro's number and formula mass.